Coming to this chapter, circular motion. What did you learn? I'm just going to brush through this. What have you learned in circular motion?
Radius.
What's the difference between uniform circular motion and non-uniform circular motion? Yeah.
Uniform has a constant speed, but different direction throughout.
Yeah. Uniform means if something is moving around and around at a constant speed. All right? If something is moving around and around at a constant speed like this, see, that is uniform circular motion. It is moving at a constant speed. Now, what is non-uniform circular motion? When the speed is increasing. That one. Okay. So when the speed is continuously increasing, that is non-uniform circular motion, and we'll talk about that in the later chapters. But right now, we're talking about uniform circular motion, where something is moving around and around in a circular path. When something is moving around and around in a circular path, so what is happening is the speed is constant, but the velocity is changing. So if you remember, I've written this, and at some other point, the velocity is v2. So clearly the velocity is changing, but the magnitude of the speed is not changing. So speed is the same. And that's why I said v1 is not equal to v2. Why? Because the directions are different. Even if this is moving at 10 meters per second, that's moving at 10 meters per second, the velocities are not the same. But the magnitudes of the velocities are the same. And that's what we call as a speed. The magnitudes are exactly the same. So there's no change of speed, but there is definitely change of velocity, which implies there is definitely an acceleration, correct? And the acceleration is v2 minus v1 over time. That is your acceleration. So acceleration is equal to v2 minus v. Acceleration is also vector quantity. But if you are looking to find only the magnitude of the acceleration, then you find the magnitude of the v2 minus v1 and then divide by time. So that will give you the magnitude of the acceleration in circular motion. And in connection to that, we saw the other, before we went into accelerations and stuff like that, there are a couple of things that you need to be clear with, some terminologies. As you can see here, this is the radius. And this is the, what is theta called?
Angular displacement.
Angular displacement. Good. Theta is called the angular displacement. And then you can see there is a distance covered along the arc. That is the arc length. There's a distance covered along the arc, which is called the arc length. And this is the angular displacement, angle. And what is angle defined as? What is angle defined as? Yeah.
Ratio of arc length to radius.
The angle itself is defined as the ratio of arc length to radius. Whatever be the length from here to here, divided by the radius, will give you the angle. But this angle will be in radians. The angle is in radians. That's the SI unit of angle. That is a true method of representing angles, especially when you are using that into equations. Now, we have used angles in degrees, but that is just for convenience. Even now, you know the degree angle better. To practically imagine it, degrees is better, right? So if I tell you, how big is it? Like 35 degrees. So that's 0. Maybe that is 30, 35. So that's 35 degrees, right? So you can picturize it very easily in terms of degrees, but not in terms of radians. So what is a radian? I've defined that too, Brent. Michael. Yeah. What is a radian? A radian is the angle. So this becomes 1 when these two are equal to each other. Simple. When the arc length is exactly equal to the length of the radius, then you have an angle of 1 degree, 1 radian. So 1 radian is when S and R are equal to each other. I think I've gone through all those things. You can see all that. So when you take a circle if you kind of cut off arc lengths which are exactly the same as the radius, you keep cutting off, how many of those you could cut off properly? 6. And then you have a little bit left, which is 0.28 times the radian, 0.28 radians basically. And therefore, the total angle in a circle, is 2 pi radians, which is 6.28 radians. And that's where the pi is, 3.14 is used there. So when you say 2 pi radians, you're using the pi on the calculator, pi. So 2 pi radians is 6.28 radians, which represents the total angle in subtended by the entire circle at the center. Clear? So we touched upon that point. Now, of course, a conversion between radians and degrees is something that you should know. So if you're going from degrees to radians, what do you need to do? You're going from degrees to radians. So divide it by 180 and then times it by pi. That will get you the conversion. And if you're going to go from radians to degrees, you first divide it by pi and then multiply by 180 degrees. You can see that. So you want radians, therefore you ultimately multiply by pi, radians. You want degrees, you ultimately multiply by 180 degrees. So think of it in any way. So the conversion is like this. Or you can do divide by 360 and multiply by 2 pi. That's unnecessary, right? So that's why I said 180 and pi. So pi is 180 degrees. Pi is 180 degrees. So that's 3.14 radians straight away. So mentioned that, and I think we did some numerical on finding out how much angle is subtended at the center of the Earth by the entire US. What was the angle? 40 something degrees. Why did we have to convert back to degrees? Is for us to visualize it, right? What was the angle in radians? 0.7 radians. That doesn't give you any picture at all. That's why we put 0.7 radians. How do you convert to degrees? 0.7 times divided by pi times 180. So that gives you 40 something degrees. So that gives you an idea. So we'd still use degrees for multiple purposes. Like even in the aviation, the heading is given in terms of degrees. Well, that is how it was, used before. And radian is not a very comfortable unit to use. Radian is not a comfortable unit to use. But scientifically, that's the correct one. So if you're actually putting stuff into equations and plugging into equations, then you have to use radians. Now, in the previous examples and all that we saw, we put sine theta, cos theta, tan theta. Those are okay with the degrees, as long as your calculator is in the degree mode. So if you're doing tan of 30, it's fine, but your calculator should be in the degree mode. If your calculator is in the radian mode, the same tan of 30 makes no sense. Instead, you should say tan of pi over 6. So 30 degrees is pi over 6, 180 over 6. So if you're putting your calculator on the radian mode and then type in tan bracket pi over 6, it will give you the same answer, 0.577 right? Now, apart from this, we also went through that equation once again. Let's go through it. So if you cross multiply this equation, we get S is equal to R theta. S is equal to R theta, which is basically the same equation as this. S is the linear distance. S is the linear distance traveled by the object from here to here. And R is the radius of the turn taken. And theta is the angular displacement. How much angular shift has taken place. And if I divide this equation by time throughout, if I divide both sides by time, some of these may not be in your notes. If I divide this with time, what is distance over time? Speed v. And over here we have r, which is a constant, and theta over t is a variable now. This is the angular displacement. Angular displacement over time is angular velocity. So we have r omega. Now, try to call this the way it is called, omega. So omega. Don't call it as W and all that, as 50% of my students normally do. Okay, so just call it W for convenience. Oh, V equal to RW. It's okay as long as you're solving problems here and you're talking to me and you're saying V equal to R omega. But what happens when you go to the next level and you go to colleges and say, all right, I'm taking my physics there. So, and you're trying to tell your professor, okay, so I know this equation, V equal to RW, I can use that. And he was like, what is that? V equal to R what? W. Who taught you physics? That's the first question he'll ask you. So don't please humiliate me. So try to learn the right thing the right way. Okay? So this is omega. Call it the same way. So any of those Greek letters, they have to be called exactly how it is. Then only there will be uniformity when you talk to each other. The mu. You know, we use coefficient of kinetic friction, coefficient of static friction, and we use mu also as micro, you know, in units. So mu is to be called mu, not a backward y and all that stuff. I know some students kind of call it backward y all the time. The backward yk, the backward ys. In other words, he means mu s and mu k. Why backward y? So, yeah, don't call it by any other name that is omega. So, V equal to R omega. Now, try to investigate the units on both sides. The unit of V is meters per second. The unit of R is meters. The unit of omega is, have I not discussed omega earlier? How much? Radians per second. Now it looks like there is something messy up here. Look at that. It says meters per second here, and here it says meters radians per second. How is it possible that you have an equation with two sides of the equation having different units? It's because radian is just not a unit. It is not a unit. Look at this. Radian. What is S measured in? What is R measured in? So what is radian? Nothing. Radian by itself is nothing. That's why radian is put as a subsidiary kind of unit. You know, when you listed the basic units, we put radian at the very end. There is a reason why radian was considered at the very end, because it is literally not a unit. It's only a symbolic representation of the fact that you're talking about angle. Because if you don't say radian, what are you calling it? You know, you have to call it something. You can't say the angle is like 50 what? Is it 50 degrees or 50 radians? So to differentiate it, you have to say something as radian. So radian by itself does not make any sense. It has no unit. So having a radian sitting there is not going to make equations messed up. So this radian basically means nothing. So don't worry about that. And then you just focus on meters and seconds. That's it. You get it? And coming to omega, what is omega? Omega is theta over t, the angular displacement over time, and this of course is measured in radians, and this is measured in seconds, so it's radians per second. So omega, which is called angular velocity, radian is angular velocity, which is measured in radians per second. Is that clear? And so omega is theta over t. Now, if an object is going from here to here, then that is theta. If an object goes from here and goes all the way around and comes back again to the same spot, what is the angle? 2 pi. So this becomes 2 pi. If you're talking about one full turn, it is 2 pi. From here to here is 2 pi radians. And what is the corresponding time called? What's the corresponding time called? The time taken for something to go once completely and return back to its original position is called. It's probably a new term for you, but you must have heard that anyway. It's called a time period. It's symbolized by the letter capital T. We use capital T for tension and all that. But then that was in mechanics. Now here in circular motion, T can stand for time period. That's why some books actually differentiate tension as Ft, force of tension, instead of just calling it tension, just Ft, so that makes it kind of different. Alright, so 2 pi is the total angle in one full turn, and T is the time period, which is the time taken for one complete rotation, one complete revolution, one complete cycle, one complete of anything. That is time period. So what is time period? Time taken for one complete circular motion, one complete rotation, revolutions, and all those things. So that is the time period. So T seconds it takes for one cycle. T seconds it takes for one cycle. Why is a cycle called a cycle? Yes, you're actually like using your feet and cycling the pedals. 1, 2, 3. You're cycling. Recycle. Recycling. This paper. Take the paper. Take it. Crush it. Grind it. Make it pulp. Make it paper back again. Bring it as a textbook in front of you. That is recycling. So it makes one cycle. Right? The word cycle is clear, right? So we use it in biology also. What's the cycle there? Life cycle. Life cycle. Okay. So T seconds it takes for one complete cycle. So in 1 second, how many cycles? If in T seconds it completes one cycle, in 1 second, how many cycles? Now, many of you are totally confused upon that question, so I always have to do it the other way around. $5, you get one cake. $1, how many cakes? Look at that, so fast it is. When it comes to dollars and cakes, your answer is so quick. But when it comes to variables, you're totally lost for some strange reason. So T dollars, you get one cake. So $1, you get how many cakes? 1 over Tth of a cake. Simple as that. And that is 1 over T. So whatever is happening in 1 second is 1 over T cycles per second. So T seconds it takes to complete one cycle, and in one cycle, how many cycles are made per second? It is 1 over T, and this 1 over T is also called with a new variable which is F, called, what is F called? Frequency. That's called frequency. How many cycles are completed per second? That's called frequency. How many rotations are completed per second? That's called frequency. How many revolutions are completed per second? That's called frequency. Frequency is a number of cycles per second. So what is the connection? F is 1 over T. And T is also 1 over F. F is 1 over T and T is 1 over F, the reciprocal of each other. So what is the unit of this? Look at that. What's the unit of F? What's the unit of F? 1 over second. So the unit of F is 1 over second, or second to the power of minus 1. Or instead of writing all this junk, you just say or hertz. Okay, frequency is measured in hertz. So instead of writing second to the power of minus 1 or per second, you know why I'm not including cycles? Because cycle is not a unit. It is how many times and like how many one complete path. Frequency, the term frequency, we use it multiple times. Like for example, a bus, say bus number 25. You get bus number 25, and the bus comes back again the same spot. How long does it take for it to go and come back? That's called time period. How many buses you can get per hour? That's called the frequency. You understand? Like that's what you say, like, oh, bus number 2. How frequent is that bus? How frequent is that bus? You're using the term there, frequency. Oh, the frequency of that train is pretty good. You get 5 minutes, one train. So frequency basically relates to how many per unit time. But SI unit of frequency is how many per second, right? That's called frequency. What's the frequency of your car engine when you're normally going at 70 miles per hour? How many cycles? Now, you don't normally use those things, you use RPM, right? So, how many? 2000 RPM, normal speed? Or 3000, which is on the higher side? If you're kind of going uphill, it will go to 3000 also. So, let's say if the RPM is, so 3000 RPM, it is basically 3000 revolutions of your engine per minute. Well, that is not an SI unit of frequency. This is frequency. That is frequency, but the unit is totally not favorable for us. And if you're going to use this frequency into your calculations, you can't use this number. So what do you need to do? Change it. 3000 revolutions per 1 minute. What's one revolution in radians? Oh no, you don't have to change the revolutions. Just change the time. Just change the time.
Times 60.
So 3000 revolutions, which is basically like cycles, per 60, which is how many hertz? Which means what? 50 times a second. When you say your engine has already gone 50 times, pretty fast. So 3000 RPM is like really reaching out too much. So 50 times this thing is spinning every second. And for everything that is spinning, there is a force involved. So when I'm spinning this, there's a force involved. Now that's what the last thing was when I discussed about centripetal force and all that, right? So when I'm spinning this, isn't there a force here in the string trying to pull it? Now when I increase the speed, what's happening is that force becomes tremendously high. Now each engine part which is spinning at this frequency, it will really undergo a lot of tension in the parts. So if you're going at tremendously high speeds, you're expecting a lot of force within those components, and sometimes it can go over. That's why you have in the RPM meter, a big range of it is in red, indicating that if your RPM kind of goes there, you are damaging your engine. But it won't damage immediately. There's a chance that you can get it damaged in that area. So when you're raising it to that point, there is a chance that you may have the engine spinning at higher than normal limits, which can damage the parts of the engine. So safest RPM is like between until 3000 is fine. Until 50 hertz is fine. 50 hertz is a lot as well. 50 times something spinning per second is pretty fast. When I was spinning this, was it turning 50 times per second? No, not at all. It could be like 2, 3, or 4, 5 maximum. 50 times per second, this will snap. Even with these keys, the force that is expected of this is too much that it will snap. So if I connect this to something that's going to spin at 50 hertz and just turn it on, you will see the keys flying away. Because this material is not good enough to take 50 hertz. So that's why there's a lot of torture that's going on the engine parts. Okay. So you understand frequency and time period. And of course, so what is omega? Omega is the angular velocity. So how do you find it out? Use theta over t. What is the angular velocity of the seconds hand of the clock? Do that before the bell rings. What is the angular velocity of the seconds hand of the clock? Anything that is spinning like that has to have an angular velocity. That second hand of the clock is going through one turn in how much time?
60 seconds.
60 seconds. And how much angle?
2 pi.
So 2 pi divided by 60
Negative
radians per second. Not negative.
Well, it's counted.
So 2 pi divided by 60 is what? Point? Whatever.
Wait.
Yeah, 0.1 something.
Wait, isn't it negative?
No, why is it negative?
Because it's going.
Oh, clockwise, counterclockwise. Yeah, you can just ignore that for the time being. For the time being, sign conventions can be kept aside. So yes, he's right. The angular velocity of the second-hand clock is negative because it's going clockwise. When something spins round and round with uniform speed, but with changing velocities, right? That is what we regard as circular motions. For the time being, we are going to talk about uniform circular motion. And for uniform circular motion, some of the common equations. So you know this. All right, so we have an object going round and round, so it has a velocity v1 and it has a velocity v2 over here. The magnitudes are exactly the same, but the directions are different. And I've given you all the information earlier, so I'm still writing it down. V1's magnitude is V2's magnitude is V, which is called V. What is V called?
Speed.
Speed. It's the same symbol we are using for speed and velocity. The same symbol we're using for speed and velocity. But then the difference between this and this obviously is that the vector sign is missing, right? So this is a scalar quantity. Speed is a scalar quantity. So the magnitudes of these are exactly the same as V. And then what we saw after that is we kind of defined what is the angle. What do you call that? Theta? What's the physical name for it?
Angular displacement.
Angular displacement. So theta stands for angular displacement. Understand how these are called and use them the right way. So theta stands for angular displacement. And angular displacement is measured in radians, right? Always is measured in radians. Now you can see I put a little arrow like that, indicating the angle, because all angles are measured from the positive x-axis. So when you have something measured from the positive x-axis this way, we call the angular displacements positive. Remember, angular displacement is also a vector quantity. Theta is a vector quantity, which means it may have sense of direction. It has sense of direction, right? So in sense of direction is counterclockwise, positive. Clockwise is negative for you, okay? This is counterclockwise for you. And that is clockwise for you. So if the angles are measured from the positive x-axis counterclockwise, those are positive angles. How many radians? From here to here. Pi over 2. Another pi over 2. Another pi over 2. Another pi over 2. Total of 2 pi radians. So that's how angles are measured. So angular displacements can be positive, can be negative, it depends. And then what is angle defined as? It's a ratio of arc length to the radius. We went through all this. I'm just putting everything together again so that you can go faster in your thought. So theta is equal to S over R. And that's how you can actually connect the angular displacement with the arc length and the radius. And if you cross multiply, you get S is equal to R theta. Gives you a connection between, again, how much is the arc length if you know these angles and the radius. Alright. Dividing both sides by time on this equation, we have linear speed. That's a linear speed. Like how much distance in how much time. So if it takes t seconds for it to go from here to here, if it takes t seconds to go from here to here, then S over t is basically the distance over time, which is speed, and theta over t is called omega, and what is it? Angular velocity. Angular velocity. Yeah, we'll get there. So V is equal to R omega is the connection between angular velocity and linear speed. V equal to R omega. And I think we spent some time calculating the angular velocity of the seconds hand of the clock, right? So is it positive or negative? It's supposed to be negative because it's clockwise. Clock is clockwise, okay? So the seconds hand is going this way, clockwise. And so they're all negative. So whatever calculations you did, it's supposed to be a negative number because it's spinning. Now, spinning clockwise or counterclockwise depends on the way you look at it. If you look at the same clock from behind, it's going to be the other way around, right? So you take the signs according to what you see. And once you keep a convention that, all right, this way is positive. For me, this way is positive. And so you stick to that all the way through the problem. So if I'm going to take this one as negative, for you, it looks like it is positive, right? Because when you're on opposite sides of the spinning object, it will look totally different. Yeah, so we have to take the sign conventions according to how you see it. All right, so V equal to R omega. Omega is the angular speed, okay? And V is a linear speed. So there is a connection between angular speed and linear speed. How fast is something moving? That is linear speed. What is the angular velocity? That is m. All right? To give an example, if there's a ceiling fan that is spinning, which part of the ceiling fan has a larger angular velocity? Which part of the ceiling fan has a larger angular velocity? Which one has the tip or the middle part? Which one has more angular velocity?
Yeah.
Someone said the answer. Can you say that loud?
None of.
No? All of them are same angular velocity. Because the whole thing is spinning. So if one part of the fan goes through 2 pi radians, all the other parts must have followed, right? So therefore, the angular velocity is exactly the same. See, this is the blade. This part of the blade and this part of the blade, they're all spinning together. So if it goes once completely around, all the parts of the fan has gone once completely around. And therefore, the angular velocity of the fan, the whole fan system itself, is going to be a fixed number. Constant, everywhere. But which part has the highest linear speed?
Tip.
The tip. So if you're going to poke your finger into the fan, which is a safer place to put your, you want to stop sometimes. You want to stop the fan urgently, right? An example is in my house, my son was having budgerias, he had in his room, and sometimes he lets it free, so I just enter and close the door, and once I entered the room and I just flipped the lights and fans on, I didn't realize they were free. So the fan started working. And then I realized the bird was free, and he just started flying this way. And I didn't have any other time to, you can't wait for the fan to come on its own to rest. If you turn it off, that's not enough. So I had to rush, jumped on the bed, and just stopped it. Now, where do I stop it? At the tip or the middle? The middle. Because it's safer to kind of put your hand right in the middle because you know it's going slow. But if I try to touch the tip of the fan, that is inviting trouble, right? Because tip will be going faster. So the further the end, so you can see when something is spinning like that, this part is right close to center. How fast is this part moving? The center itself. It's hardly moving because the center is right there. It is just like revolving around itself. It's not moving at all. Whereas these things are moving faster and faster and faster. So this is going with a certain speed. This is going with a higher speed, higher speed, higher speed, higher speed. And the speed is directly proportional to how far it is, right? V is directly proportional to R because omega is a constant. Each and every part of the fan blade is moving with the same angular velocity. Therefore, V is purely dependent on the distance from the center, right? That is the radius. So, which part moves fastest is, of course, the tip is moving faster. And the same applies to the Earth. If you look at the Earth, these are the poles. That's the equator. Now, who on the earth is moving fastest? Probably somebody on the equator. So somebody on the equator is going around like that, you see? He's going around one full turn in one full day. In 24 hours, he's going to go from here all the way back here with a good speed. We are not going, but we are taken for a ride. Because tomorrow, same time, you should be here. After going around the world. Right? It's interesting. And we are going at what speeds? Something faster than speed of sound. We are going at a speed more than speed of sound. Think of that. Only then we can come back here on time tomorrow. But what about people here? People here are not going that fast. Because they are also having the same omega, correct? Because 24 hours, everybody is coming back. So this one is going slower. Why? Because the radius is smaller. And here the radius is higher. And people over here, they're going to be traveling shorter distance further, less and less. What about a person standing on the pole? He, in 24 hours, he'll be like going like this and coming back. He's like this in one direction, and then 24 hours it will take for him to kind of spin like that and come back. So that is what will happen to the person here. And same here. Get it? So the speed is directly proportional to how far away you are. Now if you don't like to be on a, we call that merry-go-round. If you don't like really there, but you want to accompany someone, you better take your seat somewhere close to the middle. Right? If you sit at the far end, you'll be like swinging like crazy. And so you need to really grab here and there. But someone standing close to the middle, you don't even have to grab anywhere because you're moving at a much smaller speed. Is that clear? So for circular motion to take place, we have to look into all these points, like angular speed. Is that changing or not changing? For uniform circular motion, angular speed is not changing. Right? And the linear speed is not changing. Okay, so understanding this, now going back to the definition of acceleration. Acceleration is v2 minus v1 over time. The magnitude of acceleration, which is a, is the magnitude of v2 minus v1 over time. Why can't I take it as v2's magnitude minus v1's magnitude? Because these are exactly the same, so it will come out 0. So v2 minus v1's magnitude divided by time gives you the acceleration of the object. Now to understand that better, we have to find out v2 minus v1. You know how to subtract vectors, right? We do vector subtraction the same way as you normally do. Now here is one vector v1 and the other is the next vector v2. Now we are assuming that these two vectors are not too far away in terms of angular displacement. So we are assuming that the angular displacement is very small because what is acceleration? Is a rate of change of velocity. And when you say rate of change of velocity, the time is supposed to be tiny. Okay? Rate of change of something is time. You're not going to take 5 minutes as a time. It's going to be fractions of a second. That means in fractions of a second, it's going to move from here to probably right there. But will the velocity be different? Yes. But you won't be able to see it. I drew it pretty wide over here so that I can represent on the diagram the angular displacement theta and so on, right? Right? So I can draw all those things, but in reality, this v1 and v2 are supposed to be so close. But if I draw the real diagram, like this is v1 and that's v2, you won't see it. There's a difference. You can't even see that angle because it's supposed to be so small. And just to make it clear for you, I'm just drawing a diagram that's big enough. And so when you're discussing about, so understand that theta is supposed to be very small. So theta and t are very small. Alright, so when theta and t are very small, how do you get the accelerations? Like how do you do v2 minus v1? Yes. How do you get v2 minus v1 vectorially? What you do is draw vector v1 first. So v2 minus v1. So you want to do v2 minus v1. So when you want to do v2 minus v1, it is v2 plus negative v1. That's what basically we want to do. And how do you draw that? Draw v2 first. Here is v2. That's v2. This one. I've drawn a little big, but that's v2. And adding what to v2? Negative of v1. So basically it's this. That's negative v1. Now, if you add v2 with the negative v of v1, we get v2 minus v1. And where is it? It's right there. So v2 minus v1 is right there. v2 minus v1 is right there. And what's the angle between v2 and v1? It is the angle theta that is here. This is the angle between v2 and v1. Right, Michael? v2 minus v1's the angular separation is this, and here is v2 minus v1. So the length of this line is supposed to be the magnitude of v2 minus v1. The length of this line is supposed to be the magnitude. So what I'm looking for is exactly that. We want the length of that one. How much is the magnitude of v2 minus v1? Now, to get the magnitude of v2 minus v1, we're going to use another small angle concept. And the small angle concept is this. When the angle is very small, this line that is drawn here, it looks like, it is actually one side of a triangle. But when the angle is very small, that one side of the triangle or an arc will make no difference when the angle is very small, correct? Like this. When the angle between two lines is very, very small like that, what's the difference if I just make a connection by an arc length or a straight line? It doesn't make a difference. It will be pretty much the same thing. So when the angle theta is very small, this arc or a straight line cannot be differentiated. But if the angle is big, arc length and a straight line can surely be different, right? This is definitely not the same length as this. So over here, it is a straight line. It is not an arc length. But we can assume it's going to be an arc length. Why? Because we are assuming the angle theta. We know that the angle theta is quickly changing angle, and the time corresponding to that is also very short time. So that is what it is. So this length of this, the magnitude of v2 minus v1, is almost like the arc length, assuming that this whole thing is like a sector. What's the magnitude of this line? V. What's the magnitude of this line? V. It acts like a radius. It will act like a radius. This V and this V are acting like radii. And that is the arc length. Okay, so this is like the radius, this is like the radius, and that's the angle theta. So we have S is equal to R theta, that concept. So I'm going to use the idea of S is equal to R theta concept over here, but S is this, V2 minus V1's magnitude is equal to, what is R in our diagram? V. And what is the other one? Theta. So this part is simply the product of linear speed and angular displacement. Get it? So I can now go back to the acceleration. I'm just going to substitute v2 minus v1's magnitude as v theta. What is theta over t? Omega. So then now we have an expression for acceleration as v omega. We have an expression for acceleration as v omega. Now this acceleration magnitude is v omega. Of course, the unit is meters per second squared, just like any other acceleration. The unit of rate of change of velocity is meters per second squared. So this is an acceleration. What is v? It's a linear speed. What is omega? It's the angular velocity. Some people call it angular speed as well. So if you see angular speed being used, just take it as omega. What's the unit of linear speed? Meters per second. What's the unit of angular speed? Radians per second. So what is acceleration? V omega. Understand this? This is the acceleration which is equal to v omega. And we call this acceleration centripetal acceleration for a reason. What's the direction of that acceleration? See, you saw the vector diagram, right? This is v2 and that's v1. And the resultant was here this way. Which way is that resultant? Which way is v2 minus v1? Which way is v2 minus v1 directed? Towards the center. So we know that the acceleration's magnitude is v omega and it is directed towards the center. And we call this centripetal acceleration. Centripetal acceleration. And what is centripetal acceleration? It is the acceleration that is needed for an object to go in a circular path. Okay? That is the acceleration that is needed for an object to move in a circular path. We need that acceleration. Now, since you know v equal to r omega, if you take this v equal to r omega and substitute it there, if you take the v equal to r omega and put it into that equation, we have centripetal acceleration also as how much? This is r omega getting in place here. So r omega squared. So that's another equation for centripetal acceleration in terms of angular velocity. So this is the radius and that is the angular velocity. So centripetal acceleration is also that. Now if you take omega, since omega is equal to v over r, if I take this and put it there, I have another equation. What is that centripetal acceleration? Bill, what is this? If I take omega and put it here, what do you have? Yes, Bill? V squared over r. So centripetal acceleration can be seen in different formats. Now here are the three formats. And you can see they're all the same thing, but having different variables. Now this one has got linear speed and radius, which is a very common thing. When something's moving in circles, you are associating it to the speed. How fast it's going, what's the turn radius. If you know the angular velocity part of it, then you can use that equation. Now if you know the linear speed and angular speed and nothing about radius, then use that. Okay? Out of these three equations, this is the most commonly used equation. The most commonly used equation for centripetal acceleration is this. The next one is here, this one. This is hardly used. Okay? So you will end up using this and this. Most of the time, like these are mostly used for things that are spinning, like Earth spinning round and round with a constant angular velocity, those kind of things. So normally in gravitation this is used, but this is a very commonly used equation for centripetal acceleration. And what causes an acceleration? What will cause an acceleration? Yeah. A force. So you need a force to create an acceleration, and that force is called centripetal force. So centripetal force is m times the acceleration, mass times acceleration, Newton's second law, right? Mass times acceleration, v omega, or m r omega square, or m v square over r. Any of these equations will work. So centripetal force can take any of these forms. As I said again, this is the most commonly used one. mv square over r is a very commonly used expression for centripetal force. Now, what is centripetal force? It is a force, yeah.
It is the force that basically it has a rotation, a revolution that keeps it spinning perpetually.
Yep, not perpetually, but yes, that is the force that is needed for something to go round and round in a circular path. Okay, if something is moving in a circular path, then you need that force. If you don't provide that force, it cannot go in a circular path. You get it? Now, let me give you some examples. Here, this thing is spinning around and around, right? What is keeping these keys going round and round? Where is the centripetal force in this scenario? Huh?
Arm.
The keys. I'm not touching the keys. What is the centripetal force?
Here.
Tension. The tension in the string or the lanyard is what makes the key go round and round. If this thing snaps at any point, what will happen is the key cannot continue to go in a circular path, so it will just fly off tangentially, right? Okay. So what is providing the centripetal force here is the pull towards the center. This is the center. That's a center. And the keys is the mass. So we have mass, we have the speed with which it's moving, and we have the radius. Now, if I spin it faster, same radius, but I'm spinning it faster, what do you know about the tension? It's greater. And what if the radius is smaller? Radius is smaller. The force required is greater. So you can see centripetal force is supposed to be bigger for a smaller radius and for a higher speed and for a bigger mass. Right? You can see all three factors coming in. So what keeps these keys going round and round in circular path? One word answer, the tension in the cable or tension in the string. What keeps an electron go round and round the nucleus? The electrostatic force of attraction between the positive nucleus and the negative electron. We get it? That's the electrical force. So what keeps the electron spinning round and round in circular path around the nucleus? Why can't it just get inside and then get attracted? Why is it spinning round and round? Is because the centripetal force over there is provided by the electrostatic force of attraction. What provides the centripetal force for the moon to go around the earth? Gravitational force. The gravitational force of attraction on the moon by the earth is supposed to be what keeps it going on and on. What provides the centripetal force for the earth to go around the sun? Also gravitational force. Right? Gravitational force is what is responsible for keeping the earth in orbit. Or satellites. What keeps the satellite spinning round and round in orbits? Gravitational force. And we'll see that how we transition from circular motion to gravitation in this manner. Okay? Because gravitation is basically circular motion. It is circular motion. We're just learning a little more of about the planets and satellites and stuff like that. So we'll focus our attention on the angular velocity of this, the time period, and how fast is it going, and how fast should it go at this particular height. So once you focus like that, that is the chapter of gravitation. All right. So centripetal force is needed for something to go round and round in a circular path. You saw many examples. Now I'm going to demonstrate something and tell me where the centripetal force is in my demo. I'm walking straight. I'm walking straight and I'm going to take a turn to the right. So just watch. I'm walking straight and I turned. Did I execute a circular motion somewhere? Where? Where was it? Right at there? I was going in a circular path. What made me turn?
Yourself.
Myself. Friction. Friction is helping me walk forward. Without friction. So when I'm walking like this, how many forces are acting on me when I'm walking like this?
2, 3.
2,
Gravity.
4. Which are the 4?
No reaction.
Normal reaction acting upward, the weight pulling me down, then the traction force forward, right? Traction force is a friction force, remember that. So what is helping you to walk is friction. So there's a saying, without friction there's no traction. So to go forward in life, you need to have some friction somewhere. Makes sense, right? Yeah, you can't just go forward in life very easily. You have to struggle hard. You'll have a lot of friction to overcome. And after that, you see how you're getting. Now, if you're afraid of those frictions, and if you keep away from friction, then you're not getting any traction from it. All right, just keep it in mind. So without friction, there's no traction. So yes, there is a traction force that is making me go forward. So how I'm actually like going forward is because of the traction force. Which way? What helps me walk is that way. Friction is that way. Because that's a traction force. See? What is helping me walk is a friction on my feet in that direction. That is what is dragging me that way. That's what we call as traction. What is helping your car move forward? Traction force. Provided by the road on the tires. Which way? Forward. Nothing can move forward without that traction force. What else? Now we got covered up 3. Weight, normal force, the traction force that makes me forward, and what is here?
Friction.
Friction, the air drag. The drag force is not the friction at my feet, because the friction on my feet is what makes me go forward. What is pushing me backward is the air resistance. Although it is something that seems to be light, it is something that is a big thing. Air resistance. Air offers a big force on you backward. Cross-country runners, you know this. Or sprinters. Are they not applying a traction force forward as they're running? So if you think of a runner, weight, normal force, perfectly balanced. Traction force, they're applying traction force to make themselves go forward. If that's the only force, then they should be accelerating forever. Cross-country runners should be going faster and faster and faster and faster because it should be acceleration forever. But what's happening is that once you gain a certain speed, the fluid drag forces come in. And because the drag forces are coming in, your maximum traction that you're applying forward and the drag forces kind of cancel each other. And then the net force becomes 0. And so you can't accelerate any further, but you can coast with that high speed. Now, how much traction you can apply forward, how least of a friction can you create in that particular situation, those things matter. So if I'm going to wear these kind of clothes and run, I'm going to create a lot of drag forces. That's why runners need to be like dressed up with the clothes that are just kind of tight-fitting, better, not fluffy ones. And if you're swimmers, yeah, also same thing. You're trying to put all your effort, so the water is pushing you forward, but what is dragging you backward is the drag forces from the water. Now, you can reduce the drag forces by wearing the swim caps and stuff like that, take away body hair. I don't think any swimmer will be having beard and all that in swimming, because that's a drag. That's going to drag. Have you seen anyone internationally? No? They'll shave their head off, and most of them will be like trying to be as smooth as possible and as muscular as possible. You need both. You need to be kind of compact and muscular. Anyway, so there is a centripetal force needed, and in this scenario, where is the centripetal force? It's none of these 4. It's none of these 4. Tell me where. So when I'm taking a turn like this, what is the force that makes me turn? Yes, because the 4 forces that we mentioned, they are still there. They're still there. But there is definitely a 5th force that's coming in. while I'm making the turn. That is what helps me to turn. Which one is it? Say it again. What is providing the centripetal force? Yes, you're right. Centripetal force is there. Which way? Which way is the centripetal force when I'm taking a turn like this? Like this is my turn. So which way is the centripetal force? Centripetal force is always towards the, where's the center of this arc? It's a 90-degree angle arc. Michael. So he is the center. So I'm spinning, it's almost like a cord is attached to me, and then he's pulling the cord and I'm just keep moving like that. But there's no cord in this situation. So what is providing that centripetal force which is vital in making me take the turn? Huh? Someone said something. Someone said something. Now, to make you understand that, let me give you another example of the same situations. Knowing that I'm trying to demonstrate this particular thing, Michael throws some soap solution or oil or something on the floor, just to see how my demo goes. So I don't know what is happening on the floor. I'm anticipating that everything's okay, and I make that turn. What will happen? I'll just keep going straight. Why? Because the force that I was anticipating to be present was gone. It's not there. What is it?
Friction.
Friction. It's a friction on my feet in that direction. There's a friction on my feet in that direction. So when I'm taking a turn like this, when I take a turn like that, at this point, there is a friction acting in that direction towards the center. That friction is a friction on your feet by the ground in that direction. It's totally different from the traction force that makes you go forward. It's totally different. This is a new force that's coming in. And that new force is needed. Without this new force, you can't change the direction. And so what will happen is, I may be going like this, and I want to turn. Physically, I may turn like this, but I'll keep going. You'll just keep skidding. Same with the car. What helps your car turn? Friction. Don't say steering wheel, driver. They can't do anything without friction. What turns the car is not a steering wheel. You ask this question to anybody, they'll all fail, because the first thing everyone says is, what turns a car? Steering wheel? No. Then what else? The person? No. The engine? They'll try all sorts of things. They won't think about friction, because that's a vital thing. Now, if it snows, and if you're driving a car on a snowy road or icy road, you know what I'm talking about. So if you're driving on a icy road, you want to take a right, the car won't go right, because it says, no, I don't get the required centripetal force, so you keep going. So your steering wheel turns, your wheels are like this, but your car will keep scooting this way. Don't get into that trouble, okay? So centripetal force is needed for the car to take a turn, and that centripetal force that is needed to make the car turn depends on what factors? Speed. Very important factor, speed. You can see that it's getting squared. It's getting squared. So if you're going a little fast and you want to make a turn, you're asking too much from the road. You're demanding too much centripetal force from the road. And the road will say, no, I give up. Because it has a limit. The friction has a limit, right? You know that. The limiting value of friction, what is it? Equation? Mu s times normal force, yes. Mu s times normal force. So there's a limit for friction. And if you ask more than that and say, oh, I can't reduce my speed, I have to go at that speed, well, then the friction will say, all right, go to hell. All right, so therefore, it won't be able to pull your car, and then it'll start skidding. Make sense? So that is one thing. What is the other thing you can do? To have less friction demand. Take a wider turn. That's right. Take a wider turn. So if you're actually making a left turn on a road where you have 2 lanes, take the outer lane. That's better for you. On a slippery road, take the outermost lane. And then what will happen is you're not demanding too much friction from the road. On a normal day, it's fine. On a normal day, the friction is far more than what you can think of. So no matter what you do, the car will pretty much stay in the same place. But you can't always anticipate the same conditions all the time. Like you're riding a bicycle and you go home taking a turn very nicely. Every day you do that, but maybe a sand truck or something went before you and dropped some sand on the way, and the place where you're actually supposed to make a turn is now having a faint coating of sand. You didn't expect it. And you're just making a normal turn just like every other day. And what happens?
Slips.
Slides and goes. Because that little layer of sand, the presence of that little layer of sand kills off the friction. And so the friction is not able to help you make that turn complete. And so you slide and fall, and then you'll say, oh, what happened? Accident. Well, you got to be looking around and seeing what is the condition of the road every now and then. You can't just be like totally ignorant about that fact, because that's the most important thing that keeps your car, your bicycle on the road as you want. Nothing else. So when you're looking at the road conditions when you're driving, you see a puddle of water, take care. Is it wet road? Okay, take care. So the only thing is, can you drive your car on a snowy situation, icy roads? Yes, but take care of that. On a normal day, you make the turn possible at a speed of 20 miles per hour. But on that particular day, you may have to go like 3-4 miles per hour. Don't go more than that, because what is 20 squared? 400. What is 2 or 3 squared? So you see how much it impacts. It impacts a lot. If you put 20 miles per hour and then square it, it's like 400. Versus when you're going at 3 miles per hour, it's like 9. So the demand you're putting on the road is not too much when you're going at 3 miles per hour. So you can make that turn complete beautifully without skidding. Yeah. The snow can help you grip, but not too much. That's one of the things. The radius is something that you have no complete control on, but yes, the inner lane, outer lane can make a difference. That can make a difference. If you try to take the inner lane, you're demanding a little more friction from the road. You get it? So for anything to turn, make a turn, you need a force, and that force is supposed to be the net force. So centripetal force that is needed is the net force. Why I'm saying it's a net force is because, so when I was walking like that, how many forces were acting? When I was taking the turn, how many forces were acting? 5. Out of the 5, the vertical ones are gone, cancelled, right? The forward traction and the backward air resistance gone, cancelled. The extra thing that came in was the friction. That is a net force. So you can have thousands of forces acting on an object which is turning, but it is the net force that is needed. So in any case, when something is going round and round, you may be finding so many forces acting on it, but the net of those forces must be provided. If that is provided, then it will make a turn. Now, there are issues with this extra force. What are the issues? Now, think of this. I'm standing like this. There's a traction on my feet that way. There's an air drag backward. And since the air drag backward is not on my feet, the air drag backward is not on my feet. Where? So this is me. The traction is here. The air drag is here, mostly. The weight is here, and the normal reaction is there. Now, can you see something is wrong there? What do you think is going to happen if an object like that is being pulled from here and pulled from here? It's going to fall. It's going to fall backward. So what do you do when you walk? Lean forward. So when you walk, you're kind of leaning forward to compensate for that thing. So these two forces are trying to tip you backward. But what you do is, as you walk, like you lean forward in order to not tip. Now think of the other force. This force, the friction on your feet. Now imagine I'm standing like this. I'm standing on a rug, okay, or a piece of carpet. I'm standing like this, and imagine someone just pulls the carpet from there. What will happen? I'll fall this way. And that's pretty much what can happen in that scenario. But I prevented that fall. How? Did you see how I walked? How I took the turn? I didn't take the turn standing straight. Watch. When I'm taking the turn. Do you see how I was leaning? You got to lean. You can't just walk straight like that and take a turn like this. Impossible. Because the friction is pulling your feet. And so the top part of the body can fall. And that's something that you all went through at different stages in life. Do you remember the first time you started walking? No, right? No one remembers. But at least you have seen other kids walking. How do they actually start walking? I'll give you a small demo. Initially, they will be crawling on their feet. First, they will be like trying to swim around, right? And then they'll somehow get onto their knees, and then they kind of use their hands and knees. That will be a stage. And after that, they will get enough confidence to grab onto something and stand. And once they stand, they'll be like, they don't know how to balance their center of gravity on their feet perfectly. So they'll be like dancing around like that, like drunkards. And then, this is a stage we all went through. I'm just kind of trying to tell you what exactly is the, and then finally, like you start walking like that, sideways, holding on to something. And then finally you have ample confidence to leave one hand and then grab one hand and then walk like that. And once you have little more confidence, you'll start leaving that hand and kind of going that way. All right? It's fine. Suppose someone is standing there and saying, come on, come on, come on. And then they'll leave their hands and they'll start walking like that. They balance perfectly and they walk. But suddenly someone calls them from this side, come on over here. And then what they do? They just turn and they fall. You know what I'm saying? Now, they're taking they're walking fine. And they're taking a turn. What was wrong there? They didn't lean. And so they just fall this way because of that attempt. Now, after some time, someone will call from here, and then they turn like this, they fall this way. And after some falls, back and forth, they'll come to know that, all right, every time I'm turning, I'm falling, so kind of be watchful. And so they start leaning a little more, and it comes like that. Same with riding a bicycle. No one can say, I just hopped onto the bicycle and just went off. No one actually I didn't fall at all. No. They're all lies. You will definitely fall. Even pushing the bicycle, you may fall. Not riding a bicycle, even pushing. Given a bicycle and just push it, and you'll fall. You know why? Because when you want to turn the bicycle, you're only turning the handlebar. So that's what happens. Someone puts you on the bicycle and then pushes you for some time and then lets you go. The bicycle is going fine. Actually, the bicycle can balance on its own. It doesn't require you. It can balance on its own, right? Because if you push a bicycle fast enough and leave it, it'll keep going. There's no need of you being there. So what is exactly happening? You go straight. Now the time to turn. You turn left. You're turning the handlebar like that. And what happens? You fall. Turn the handlebar right, you fall. And after many falls like that, then you'll start saying, all right, every time I turn left, I'm falling this way. So let me just be watchful. I don't want to fall. So you lean. You lean through a certain angle. There's a particular angle you should be leaning with. And we can calculate those things later. But the angle of leaning is something that is definite. But we don't sit down and calculate those angles. We just do it by instinct. Because you know that if it is too much of an angle, you're going to fall inward. If it is too less of an angle, then you have a chance of tipping over, right? So we just calculate those angles in our mind, basically. That comes by instinct. So if a football player is running with the ball, you don't you don't run straight and then turn like that. No, you are tilting. Sometimes when you have to dodge somebody, you tilt. You're tilting like that and tilting like this, right? Now, are you sitting and calculating all those angle of tilts? No, it just comes by instinct. The angle of tilt. That's something that's very important for anything going in a circular path. For anything going in a circular path, you need that angle. What about your car? Okay, the bicycle you can tilt. Bikes you can tilt. Your car, you can't tilt the car. Well, in the Arab world, they could do it. I've seen them do it. They tilt their Land Cruisers. They will be driving like this, and they'll tilt their Land Cruisers like that, and they'll drive on the highway. Just like that, for the fun's sake. And they'll touch the road like this with their hands. They're leaning that much, they can touch the road like that. And I've seen this. That's why, like, if you want to see it, you can actually go to Arab drifting on YouTube. Arab drifting. Yes.
Never tried this yet?
No. Like, I wonder, like, these people with Land Cruisers, how many times they must have tried to get it right? Because, the first time you tilt, is it possible that you just do it from the first time onwards correct? I don't think so. So they're doing it with such confidence. And there are some videos on YouTube, it is amazing. One guy is tilting the car like this and driving for a good stretch of distance. And there's another guy who's coming out from the window and, changing the tires, changing the wheel. He's just unbolting the wheel, takes the wheel into the car, brings another one, and all this is happening like that. And then finally, he fixes those things, and then the car comes back. Yeah, it's amazing. Yeah, people do these things. I don't know how many times they must have got it done to. Yeah, so talking about circular motion, you'll see. So even to get that properly done, they kind of wriggle, they kind of do something like wiggling, and then they get it. Yeah, I've seen it in Abu Dhabi. Rich guys, they can do it. All right. So again, the point is, what is needed for a circular motion to be possible? Centripetal force. And what is that centripetal force? It is the net force. You can have many forces acting on it, but the net force is what basically counts, the net force. And with that centripetal force, you should be able to make the turn possible and all those. The angle of turn, angle of tilt is something we will talk about later. Now, trains, cars, you can't tilt them on the go. So what do? Tilt the road. So all those ramps, have you seen them tilted? The ramps are tilted because when you're exiting, you can see the roads are tilting like that. And the angle is calculated depending on what speed is suggested. Have you seen that board there before the ramp saying 15 or 25? I think it's a yellow board, right? No one cares about it, right? No one cares about it. It says 25, but who cares? Actually, that is the speed which will be just ideal for that angle. That means if you follow that speed, you won't feel like as if you're thrown out of the car or into the car. You won't feel anything at all. You'll be perfect. If you go faster than that speed, then you'll feel as if like you're thrown outwards. If you go slower than that speed, you'll feel as if you're sliding in. So the ramp is built already, and they built it with a certain angle, expecting you to kind of follow that speed. The radius is fixed. It's only the speed that is in your control. That's why they're suggesting that suggested speed is that. Now, most of them, they don't follow it. But if you try following it, you'll see how easy it is on the turn. The same applies to planes. Planes, when they're flying, when it's time to turn, will they turn like that? They need to tilt as well. They need to tilt like that. That is called the banking. So the planes need to bank in order to provide that centripetal force towards the center. Otherwise, it will flip.